Hello, everybody. I'm very happy to be here. I'm a very big fan of Singapore, and I like the opportunity to be here again, and I'm very proud that my talk got elected. So today, I'm going to talk about how to evade or how to write code that can pass under the radar of a static code analysis tool and manifest itself in the company. So I dare to start with a few words about my person. So you better know my past. I'm from Heidelberg in Germany, which also means that I'm not a native English speaker. Please bear with me if I make mistakes. And if you don't understand something I want to say, just raise your hand and ask. So I've been in my professional life researching ERP security for quite a while. I'm not talking about this. If you're from Singapore, I'm talking about enterprise resource planning software by which organizations organize how they operate. And during that time, I found quite a lot of vulnerabilities in SAP software and reported that to them. And I also have the audacity to talk about such vulnerabilities in public. I've also co-authored some books and been speaking at some conferences, including Hack in the Box Amsterdam. And currently, I'm a CEO of a computer company focused on SAP cybersecurity in Germany. So my current research, and that's why I give this talk, is an advanced persistent threat in an SAP environment. So in order to understand how to protect against such thing, we're trying to build one to see how it would operate, what it's required to build an APT. And one of the things that struck us, I had a talk with a CISO of a very big German company where I talked about the threats of an SAP APT. And they said, well, we are not worried because we have a code scanner. And so they believe us that their scanner would detect any APT if it comes in via source code, and they're safe. And that was the point where we started thinking on how could we actually write some code in a way that a static code analysis tool is not able to detect that it's actually malicious. So we want to be protected from detection. So an important thing I want to stress at the beginning is this talk is not here in order to point the finger at certain vendors that this tool is bad or that tool is better or worse or whatever. I just want to raise awareness that all the companies that use static code analysis tools don't make the mistake to only rely on that as their only line of defense, because if they do, they may have a problem. So we tested the techniques I will show you against several scanners, by far not all scanners. And you are, as an audience, are encouraged to use the coding examples to reprogram it to a language that works with the scanners your company is using. And by the way, who in the audience knows that the company he or she is working for is using a static code analysis tool? I count 1, 2, 3. Okay, at least. At least, that's good. So in order also to make the code examples more understandable, I had to make them fit on one screen of the slide. So I had to kind of reduce some of the coding parts. So the code may look weird in some instances, but the code is there to make a point, not to be absolutely perfect. So what's my agenda? First, if we want to know how to attack static code analysis mechanisms, we have to try to understand how the technology works and under what limitations and in what kind of environment it has to operate. So we first look a little bit at what static code analysis is, how it came into existence, and what kind of methodologies it's using. Then I introduce some evasion vectors. And at the end, we talk about some conclusions from what we have heard today. So, static code analysis was, in the early days, a means to improve the quality of code, mainly the readability, the maintainability of the code, maybe the performance of the code, the stability. So, functional aspects of the code were in focus. And only later, companies added security testing to that. So, that was not the initial design to have it used for security. So, and a static code analysis tool is usually used to compensate for mistakes the developer accidentally makes or for potential lack of knowledge of the developer in order to help make the quality of the software better. So what these tools do, they analyze certain patterns in the code, and then from that they try to analyze, well, this is good, this is not so good, this is better, and give hints on how to improve the software. Many companies I know of use a static code analysis tool as kind of a central gateway for quality. Nothing can go productive before it's scanned. And don't get me wrong, this is of course a good approach. However, it has some limitations. And the limitations are that the static code analysis tools were not designed to find mistakes that were made on purpose. No? And the big problem is that these tools do not understand the semantics. They don't understand what the code actually does. They just analyze certain patterns. Back in the 80s, when the first chess computers came out, they were very easy to beat. They improved over time, and at a certain point, the chess computers managed to even beat some chess champions, which was good because they were programmed very, very smart at that time. But still at this time, when they were able to beat the champions, some people were able to beat the chess computers, not because they were very good at playing chess, but because they knew how the chess computers operated, and by that they could play some strange chess moves to make the computer lose. So the chess computers are good for players that try to play good chess. And the static code analysis software is good for developers that try to build good software. But if you have the other side, people that try to build malicious software, they may try to do it in a way that the analysis software can't detect it. So let's look at a few examples. Some things they do is, the analysis tools, they try to find certain critical patterns in your code where they say, don't use this, don't use that. These are some examples from C. Don't use an str copy or sprintf or something like that. That's bad. However, this is trivial. You can do that with a grep, with any text editor you have. You don't need to buy a static code analysis tool for that. Some smarter things are control flow checks. For example, if something is happening, make sure that something else is also happening. If we allocate memory, we need to free the memory afterwards. Or vice versa, if you want to do something, you must do some checks before you do it. Make an authorization check before you allow the user access to certain resources. This is control flow based. And the evolution from that, another technique they use is the data flow analysis. And the data flow analysis tries to see what data comes in, which paths does it take, where does it end, and checks, is malicious or potentially malicious input ending in dangerous programming practice. So here's in order to demonstrate this, a little example in Java. I hope you can read that also in the back. So it uses taint tracking, and that means everything that comes out from the outside is potentially tainted, dangerous, and then they check if any tainted variable makes it to a dangerous function. So the source is here the get parameter, which means we read data from a web source, from a web request, username, and this taints this variable. And then the program tracks where is it going. It's going here. Here, see it again, and from there it's moved to this. And this is actually used in a print line, sent back as HTML, resulting in a cross-site scripting. So this is a sync, the print line. And if a tool sees that, that's the way basically this data flow analysis works, it will report it. Makes sense. So let's look at this in a little bit more detail. So in order to build such an algorithm, if you are a vendor, you need to know about all the potential input vectors, technically all the programming commands that read data from the outside, that taint it. You need to also know all the potentially dangerous APIs in the software, all the calls that can potentially do harm. And then you need to check, so this is the sources, these are the potentially dangerous functions, and then you need to check, is there a way this potentially dangerous input can find its way to the critical function. If that happens, boom. And in order to do that, you need to know all the commands that are used to transfer data between variables or memory accesses, and you also need to understand if a different function is called with this data, which processes it and maybe later returns it, and so forth. So again, back to the example, that means you need to know get parameter as an input, then you need to be able to understand that the equal sign copies that data somewhere else, and again here, the equal sign copies it to this, and then it ends in a sink. If you use this approach, you find a lot of different problems. And data flow analysis is not only good for cross-site scripting, it's good for SQL injection, it's good for directory traversal, it's good for command injection or code injection, for example. So this type of analysis logic is very well designed to find a lot of OWASP top 10 problems, for example. So, but now, let's assume we have built a scanner that can do that. Here's a real-life code, again Java, which is very similar to the one I've shown you. Here we get information from the outside, some input. It's stored in this variable, and this variable is then used in a select query. Not a prepared statement, it's concatenated, which means this code causes a SQL injection. So the scanner sees here's the source, it's copied here, the variable is used in this command, and finally used in execute query. There is no escaping, bad. However, then this happens. The good thing is here, tick in the box, I'm talking to an audience of experts. Is this exploitable? Is there anyone in this room that can write a SQL injection exploit with 3 characters? Anyone? Why not? It's too short. You can't. Yes, there is input, and yes, it's going into a SQL statement and it's executed, but this input is too short to be exploitable, and if a scanner reports that, this is going to raise questions on the developer side, where they go, what the fuck are you showing me here? You can't exploit that. It's only 3 characters. No way. Yeah. So obviously, this algorithm is not perfect. It can run into discussions in real life. So, and let's talk about some more real-life cases where you may have problems. The first one was the limited length. Another one is, what if your input is used in a typed language like C and converted to an integer or a Boolean variable? Is it then still possible to attack with it? Probably not, because it's even shorter than the 3 characters. Or what if all the input is on its way to the dangerous command, copied to all uppercase or all lowercase? Or what if certain characters in the input are simply deleted or replaced? Is it then still possible to exploit? Or what if we append or prepend a sequence of characters to the input? Would that make any difference? Or what if the input is coming from a safe source? I explain later what I mean by that. Or what if we only spot a dangerous command, like where we create a SQL statement, but the scanner does not see any code or outside information going there? What should it do then? What if the scanner spots some input validation or mitigation functions? It has to respond to that as well. And then there are also issues with ambiguous control flow, which means there are multiple ways from this input to the final source, to the final sink, sorry. And what should we do then if it's not clear where the input is moving? These are all problems that you have to address if you write a code scanner. So, another example, and this one goes for you. Is this a bug or is this a false positive if the scanner reports it? Again, input moved here, but then several operations happen on this input and it's finally written back to HTML as HTML to the user. Is that a bug or not? I hope you can read that in the back. So we copy it to all uppercase. We strip the lesser than, greater than, single quotation mark, double quotation mark, equal sign, semicolon, ampersand, and backslash. You need a double backslash because this ends up in a regular expression, which if you only need take one backslash, it will not understand what it is. So it actually is interpreted as a backslash. The backslash is stripped by that. So a room full of experts and no quick answer to that. So how should a dumb scanner be able to understand if this is exploitable or not? It's a gray area, it's difficult. So my opinion, it's not exploitable. If somebody thinks otherwise, I'd be happy to see how it works. But this is just serves as an example how a scanner has problems actually rating or understanding, is this a bug I should report, or is it a bug I should maybe not report? So, and now I need again your help. Let's all assume you are scanner builders and vendors. Now, what are the things you need to consider? If your tool is not behaving smart, no one is going to buy it, because if they can use a tool that does a grep, which costs nothing, your tool would not be worth the money. So you need good algorithms. And also, no customer wants a scanner that produces many false positives, because these annoy the developers, which leads to internal discussions, maybe escalations. Look, it all costs money and resources. But on the other hand, the good thing for the vendor is a false negative is something the customer will not detect. If you find something that looks strange, but you don't report it, the customer may never find out. And then the million-dollar question for you now is, if the scanner you are building finds something, like in the examples before, where it cannot reliably identify if it's a bug or not, what should the scanner do? A, drop the issue. B, rate the issue as a potential bug, saying, I find something here, I'm not sure if it's really a problem or not. It could be. Or rate the issue as a definitive bug. Now I'm interested. Please, everybody in the room, think you're a vendor, what would you do? Who would drop the issue if you're not certain that it's a bug? Please raise your hand. One person, thank you. Two? Two would drop it. Okay. I mean, to say it honestly, there is no right or wrong answer to that. We're talking about business decisions. No? There are no right and wrong answers here. Who would rate the issue as a potential bug? Oh, a lot more. And who would rate the issue as a definitive bug? Nobody. Sorry. Okay. Okay, so drop the issue is great for recognition evasion. It makes my life easy if you want to write bad code. It's bad for the customer. It's a risk, but you can definitely argue that you don't want to annoy the customer with things you are not certain they are problems. Rating the issue as a potential bug is also good for recognition evasion, which I will demonstrate later. Rate the issue as a definitive bug, as you have all observed, is bad for the vendor because it will create false positives. So, and exactly that's what we notice vendors are doing. They rate the issues as potential bugs if the tool is not certain. So the other techie stuff we have to consider if you are a vendor. Excuse me. If we build a software, we need to track the control flow of the software. When we can't run it, we have to analyze it. So, which means we have to prevent circular calls like that. Function A calls B, calls C, calls D, calls A again. So our scanner must be aware of that, otherwise the logic runs into an endless loop. Also, we must keep a little eye on memory and CPU consumption, so the scans will not take hours or days or consume memory to a point where the system does not work anymore. So, now let's put on the head of a company and think about what can we do with our resources to ideally kill all the bad bugs, like Somil said earlier, the red ones, or where the company thinks these are the red ones. So let's take a fictional example. We have a scanner that just produced 10,000 findings. We have limited budget. Where should we start? Should we start with a random issue? Probably not a good idea. But again, two questions for you. Should we start with the highest ranked issues and ranked by the tool we bought? So we trust the tool's ranking, and then we solve the problems in descending order as the tool proposes. Who thinks this is a good idea? Thank you. One person says this is a good idea to trust the tool and fix the issues depending on the ranking. Alternatively, also we use the highest rank first, but after our expert team has reviewed all the issues. Who thinks this is a good approach or practical one? Also one person. Interesting. And everybody else, I'm missing point 4. What else should the company do if not one of these 3 approaches? Any opinion on that? Okay, so it's a one-on-one between number 2 and 3. So the highest ranked and the highest ranked after expert review. But the reality is actually here, the highest ranked by the tool. Why is that? Technically, it's better to address the highest rank after expert review, because then you're sure your team understands the problems. But if we are talking about 10,000 issues, and we're assuming that it only takes 15 minutes to analyze, is this issue actually something we should address, and what ranking does it need? 50 minutes to analyze and write something about it, we would end up in 2,500 hours of work, which is translated to 312 days of work, just for knowing the ranking, which is very expensive. And a company with limited resources for fixing will not invest that. That's why companies follow always, at least all the companies I know of, the proposed tool ranking. Makes sense because it's economic. So now let's go back to the last idea we had about how do we treat uncertain issues. The majority of you said we should flag them as potential issues. And if I know now as an attacker that the company will economically fix by the impact downwards, my goal is to reduce the ranking of the issues as far as possible, because then they will be beyond a certain line under which it makes no more sense for the company for economic reasons to fix them, because they follow the tool's ranking proposal. So, and here are the evasion vectors I want to show you. There are 6 in number. Let's first start with circular calls, which is pretty much straightforward. I explained earlier, we have to keep track of control flow, which means if a function calls another one, calls another one, calls another one, and so forth, and it returns to the first one, and if the scanner doesn't understand that, we run into an endless loop. So we must find some smart way to prevent that. We must have a stop function that understands, oops, I've been here already, I shouldn't go this way again, because otherwise I'll run in endless loops and all my computing power is gone. So here's some source code. For this example, I chose the programming language ABAP from SAP, and I translate what it actually does. So we start here. We have some input, a source, which transfers outside information into this variable. We are passing this variable, the tainted one, together with a literal string x to the first subfunction. In this case, it would be function b. And this function receives 2 strings, and it checks, is the first string a literal x, which is not the case when we come in here, because the second is a literal x. It does something, otherwise it will pass on both parameters to a second function. Okay? The second function is doing nothing of particular. It just passes on its parameters, a and b, to a third function. And the third function passes both variables back to the first function with a little trick here. It swaps the two. Okay. Now what happens? If our scanner, at least that's the theory, if the scanner notices, oops, now I'm back here. I already passed that. I already came to some conclusion. I have to stop now. Because if it doesn't stop, it will go back to second, third, first. Problem, infinite loop. So it cuts and says, okay, obviously something comes in here, but I don't see it coming out anywhere. I sever the data flow. It no longer exists, it stops. The problem is just, through this flipping trick, the initial x is now in variable a, which was not the case the first time the parser analyzed this. So in this time, we follow a different control flow because the input has changed. And this different control flow brings us to the evil stuff function, which actually causes a command injection. So this simple trick, if the parser actually has some termination logic in the SCAR tool, will lead to a false positive because the tool will lose the track of the data flow. It has to stop there. The data flow is severed. But still, it's exploitable. So the thesis was, the scanner does not parse the same function twice. If we change the data flow on the second time, or the third time, or the fourth time, you can be creative here, a certain function is passed, the scanner cannot follow anymore, and it will downrank because its data flow sequence is broken. The only thing it will see in this code is an orphan sync. Only the command, it will only see this insert report, which is the sync which creates code. That's the only thing it will be able to see, but from there it sees there is nothing going in there, and the issue is downranked. So it's not, I'm very sure or 100% sure with a high impact, to there is a certain chance of a high impact, but it's downranked and overall the finding is lower. So this worked against 4 of the scanners we tested. In 3 cases, they downranked to literally to the value of almost, I'm missing the English word, to almost, it's negligible. No? It's negligible because there is no data going into this function. And only one parser didn't see it because it never came out of the analysis logic. It had the infinite loop. No? So that were the 2 things we have observed here. So this is a pretty straightforward thing to test some limits of a static code analysis tool. Go to the next one. So the next idea was, okay, if the tool needs to keep track of the control flow, if, like in the example, one function calls another, calls a third, it has to keep track of that. Now the question was, how deep can I make this call stack until the static flow analysis tool says, well, I have no more memory, I give up. I can no longer follow you. How deep can this call stack be? If you simply pass on input to the next function, to the next, to the next, to the next. Like this code does, with this, some Python script, where we have a bunch of functions and so forth to a certain limit, and we pass, again, some external input to this function and see, does it reach the system command, which will cause then an OS command injection. By the way, does anybody of you know or can guess how long can I make this chain before Python complains? How deep can the call stack be before Python says, I don't want that? No idea? It's pretty much here. 1000 is the maximum call depth, which is usable by default. You can extend that through configuration, but 1000 is the limit. So now, when we did that, we checked how low can you go? What is the smallest number that the scanner still said, I can't follow you anymore? What do you think? Where was that number in our tests? With a scanner that had the poorest performance? Any guesses? Like an auction. 50? 50. This gentleman says 50. Anyone bids lower? Or higher? 20. That was really a surprise. That you, by this simple idea of call stacking downwards, with 20 steps, the data flow was broken and the issue was downranked to almost negligible because no more data flow was there. And here's, by the way, I don't know if you can see that, the runtime error Python shows when you reach the function 1000. And curiously, it says it's the maximum recursion depth. We are not doing recursion here, we're doing call stacks. But internally, obviously, Python treats that the same as recursion. So, again, the thesis, the idea was that the scanner uses a limit for its call stack in order to not overflow its own memory, like Python also does. And the idea is then to have a number of calls larger than that, and this breaks the data flow sequence, which results, again, in an orphan sync. Only the command that is potentially evil is seen, but no input going there, therefore downranked. 1 out of 4 scanners gave up very early. We also used this code in different languages, and there are other languages, for example, in SAP. What do you think on a standard SAP system? How large can the call stack be there? We had 1,000 in Python. Any ideas how other systems process this call depth? More than 1,000, less than 1,000? Someone says less, someone more. How much more? 10,000? 10 million. We tested that. That's a hell of a call stack. And I want to see the scanner that can emulate 10 million in its own memory if it parses the code. But that's just as a side note. So, next approach. That's a little bit more complicated, so I have to explain a little bit more. We call that data laundering. When some data comes in, and the scanner sees, oh, that comes from an external source, I taint the variable. Now I have to monitor it. And what we do here with this approach, we want to launder the variable again so the taint flag is gone. But we can still work with it. So in order to do that, the thinking is, does the static code analysis tool actually treat all the sources the same? So obviously, there's a lot of different sources a program can have. User interface, HTTP requests of different kinds, FTP, emails, files in a local server, files in a local network, remote procedure calls, meaning calling software on other computers, APIs, diverse services in the network, the internal memory of a system, or even the database. Oh, sorry, the data bank would be a German word. Yeah. So let's look a little bit closer at 3 of those. Some sources and origins need to be secure in order to avoid false positives. For example, let's assume you have stored some data in a variable. Now, if the scanner would then suspect this variable is tainted, you would have a lot of discussions with the developers. And every time you read memory or you read data from a variable, you would have to verify it. Makes no sense. So reading from a variable must be safe. The same should apply to an application's memory. For example, in C, you use a lot of pointers. So you get some data, you push it somewhere in memory, and at a later time, you read this memory again and process it. And this should also be okay, because whenever you read your own memory and you need to make a validation if it's still okay, it will also cause lots of discussions with developers, because they say, what are you doing here? I can't check my data all the time for potential defects. The next thing is the database. This time written correctly. Again, a question for you. Is the data in the company's database of the product you're working on treated as secure and trustworthy or not? What do you think? Should the code scanner treat the database as a trustworthy source of data or as an untrustworthy source of data? Who thinks it should be trustworthy? One person. Everybody, two, thank you. Everybody else thinks the database should be used untrustworthy, right? Okay. Now, here's some funny thought. Let's assume your company gets a visit by an external auditor, a financial auditor who wants to audit your systems. Are you going to tell this person that you do not trust the contents of your own business database? Honestly? This will get some interesting questions in the discussion. So if you tell the auditor, oh, we don't trust the data in our database, they will never ever sign your company off. So this is a big gray area between technical guys that say it could be untrusted, but if you say that in business, might not be such a good idea. And in some instances, the database is actually seen as trustworthy by scanners. Of course, if you want to attack a static code analysis tool, you first have to check, are there any data sources, if you're following this path, where the software thinks they are safe? And we're following now the database path and try to apply some deductive logic on it. So the standard case, what the scanner does is it sees there is input from an external source. It's a little bit not so sharp, but maybe you can see that in the back. And this untrustworthy input is going to a dangerous command without any precautions, which means this is a problem. We should flag that. No doubt about that. But the next thing, we get something from an untrustworthy source, but the developer uses a mitigation function, meaning he or she uses this input in a safe way and then stores it wherever it's going. This must be considered as okay by the scanner, because otherwise you would again have lots of internal discussions. The next case is, what if there exists a safe source and we read data from it and bring it to a potentially dangerous thing? If we consider it as a safe source, then this procedure must be okay. Otherwise, we would force the developers to encode or mitigate every input from a safe source, which makes no sense. Then the source should not be treated as safe. So now if we look at this graphic, we can combine two of those blocks. If you now put number B and C next to each other, we can launder input, because we have an untrusted source which we treat in the right way to store the data in a sink. And then we read again from this same sink and bring it somewhere else to a dangerous function. This works for hybrid sources. Sources that are sources and sinks at the same time. For example, a file. I can read data from a file, I can store data in a file. Or a database, I can read data from it, I can store data to it. This is hybrid. And now the idea is, what if we have input which is mitigated or safely stored in the database? Then we have no issue here. But then we read this input, but use it for a different kind of sink. For example, a command injection. Then this part is green because it's mitigated. This part is green because it's from a trusted source. Here's again another code example in ABAP, the last one. We have others in other languages. Again, there is a source. It's a UI input put into this variable. We then copy this variable to an internal memory structure and insert this memory structure, evil, I called it evil because it contains the external input, into the database. This is part one. Dangerous source, but validated because this is a prepared statement. You cannot build any SQL injection by that. And we store it safely in the sink. Good, no problem. Scanner sees, okay, input and securely stored, End of data flow. The next thing the scanner will see, okay, somebody is selecting data from the database, which is rated as trustworthy, into a second variable, LV good. And then LV good, again, this structure, /text is used to build code, which is then a code injection. And this is also rated as okay because the source is safe. However, if you look at the entire thing, we have input going in here. We read the same input because this is the same key that we use to store it from the database. We end up with a command injection, but the scanner can't see it if it trusts the database. This is the idea. So, thesis, the scanner rates certain data sources as trusted. Now, if that happens, we can break the data flow sequence. We can launder the input by storing it into the hybrid sync source and then later reuse it. But the scanner will not understand this. It only sees the orphan sync, the command injection statement, and it will not see any external input going there. So it downranks or drops it. 2 of the 4 scanners we tested are affected by this kind of phenomenon. So you can use this again to downrank the issue. And remember from what we said earlier, downranking is the goal because companies trust in the ranking of the tool. Everything you can downrank is probably never fixed. So next idea, data replication. So like I said earlier, the scanner tries to track the data by knowing all the commands that transfer data between one memory location or variable to another, like examples in C and equal variables, or we copy pointers or content the pointer is pointing to, or we use an str copy or a mem copy. These are examples of commands that transfer input. And the scanner needs to keep track of those. If it understands all of those, basically there is no way to bring input from variable A to variable B. That's the goal. Your data flow analysis is sound if you know all those commands. Now the goal, of course, or the challenge we have if you want to break that is, can we find another way to copy data? A command or a sequence of commands that does a copy without the scanner seeing it. If we can achieve that, then the data flow is again broken. So this is the traditional way it works. Input is going through several copy commands or calls to other functions to the function. However, what if there is a way, the dotted line, to bring data from here to there without this direct connection, then the scanner loses the track. So here's an example in C. We have a main program which gets some arguments. And what it does, it actually copies the first of its arguments to the variable oric, which is a buffer of 200. And then it walks over the different characters of that input. It checks each character at a time and does a switch of the and checks what value does it have. And it says, okay, if this character is an A, we want to append an A to our replication variable. If it's a B, we append a B. If it's a C, we append a C, and so forth and so forth. And finally, if it's a 0 or the end of the string, then we also want to have the end of a string here. And finally, and that's the trick, we call a system command with the replicated data. So now if you look at this code, the red points are the points where the static code analysis tool can verify data was copied. It comes from here, it goes to oric, and I still see oric here again, but then there is no further trace of the data, it vanishes. And the second variable, REPL, so the replication, is assigned hard-coded values. So there is no way the static code analysis tool can understand this mechanism. Any human tester, if you would see this code, you would clearly say, well, obviously it copies data. Trivial, but the scanner cannot see it because you don't use a copy command, you use the case to replicate that. So, again, the thesis is the scanner does not understand the semantics. It doesn't understand what the code does, so we can find ways to replicate the data without using the commands the scanner knows. Effect, the scanner doesn't know that there is a data flow, it doesn't see it. It only detects the orphan sink again, and as a consequence, the issue is downranked or dropped. All scanners we tested are affected by this. So this, if you want to try this at home, is the most effective way, because it's guaranteed, in my opinion, to find a way to downrank. I want to see the scanner that understands this logic. If you try this with the scanners in your company and you find a scanner that can catch that, I want to see that. So where the ranking is still the same as if the data flow would be complete. Idea number 5, chunked input. So basically, the idea is, like I said earlier, there are some input vectors where the variable space is too small to carry an exploit. We agreed on that. On the first example, we had 3 characters. You cannot code a SQL injection with 3 characters. Other examples are in type languages if the input is a Boolean or an integer or another short char array. You cannot write an exploit with that because it's too short. So now, of course, we have to ask ourselves the question, if we are the bad guys, how can we find a way to use these ignored sources as an attack vector? And here's an example of chunked input, again in C. So again, we have a main function which gets a bunch of arguments passed to it. And what we do now is we loop over all the arguments passed to this function, and we cast or we convert these into integers. So the first argument may be 69. We cast it on an integer, and then we switch on the integer where we cast it on, because at this point, the static code analysis software sees that was a string of unlimited size. That's a thread. But here, I turn this string into an integer. No more a thread because too short for an exploit. But we're using this and say, well, if this integer is 0, we will append 0 to our buffer and do a system command from the buffer. If it's not 0, which is the case for all the other numbers we have, then we append this integer to the buffer, but first we cast it to char. So what we do is, let's say, for example, you call this with the values 69, 68, or so forth. We first see the 69, and then we will make that into an integer, which is no longer a thread, but we will turn that into a char. 69 is the character E, capital letter E, and then we append that to the buffer. And so you can chunk your commands through all these variables into the system without the scanner understanding what's going on. Because you use an integer as the entry vector, and the integer is safe because it's too short. However, if you use multiple integers in sequence, then of course you can create a much bigger number. But this, the scanner cannot understand. It doesn't understand the semantics. You're doing a trick by using the integer, which is treated as safe. Another variation, if you still think, well, maybe some of these scanners will also track integers or booleans. This is a much more complex approach written in Node.js. So we have a web server here, and the web server gets a request. We pass the request, and then we check what is the actual path name. What was the HTML file that was requested from the browser. And then we make a switch. We have an init case, we have a hack in the box case, a plus and a 0. So let's first look at the plus and the 0. If these are called, that causes the system to call process, either with true or false as value. And process, what does it do? It duplicates the value of the variable data, and then, depending on whether this is true or false, it will add a bit at the end. Plus plus just adds a bit at position 0. And then it checks, well, do we already have 7 bits? Then we're done. And then we convert data, which is an integer, into a string. Or we convert it into a character, and we add that character to this string. And then we reset for the next. So what you can do here, you can append bits, 1 bits and 0 bits. And these functions, this one initializes the stack, and that one says, no, I'm done, and I want to eval what I have built so far. So this is a kind of Morse code you can use by simply calling 4 different functions to inject data, which the static code analysis tool cannot see because it's not even input. In this case, there is 0 input. It's not even a Boolean. It's calling functions. And the functions, by control flow, cause effects. So let's assume in this case you want to send the lowercase letter a, which is hexadecimal 61. That would be the binary representation. What would you do? You would call init to start it. Then we would call plus every time we have 1. And we would call 0 every time we have a 0 bit. And at the end, we would call the hack in the box function, which executes a system command. No way a scanner can see that. And not surprisingly, all the 4 scanners we tested, with both approaches, by the way, the integer and this binary fiddling, they didn't see it. So you could bring in input without them seeing it, which means there is no data flow. There's just an orphan sync, downranked to almost negligible. Again, the last idea, counter mitigation. Again, this is very similar to the Java example in the beginning. We have a web parameter we read, PID, which we transfer into an internal variable. However, this time we use an escape SQL command from the string escape utils, which is a function that's designed to prevent SQL injection. What does it do? It simply turns 1 single quotation mark into 2 single quotation marks, and then they are no longer considered to be a command. The 2 single quotation marks, they are considered to be a character, and everything is safe. So so the green indicates that the mitigation worked, and the green variable is fed here into the execute query, and the scanner must see that this is no problem. If the scanner doesn't see that this is a mitigation, it's worthless, because if you find a problem, the developer fixes it with a proper mitigation, and the scanner still says it's a problem, oh, yeah, you can't trust that scanner. So that works. But the idea of counter mitigation is, what if we intentionally place the mitigation in the code, we are the bad guys, and after the mitigation, we undo it. So what we do is, we replace all instances of 2 quotation marks again back to 1, which is exactly the opposite what this function did. So at this point, the scanner still thinks it's okay because it's escaped. And then we feed the result back in here. I just made it red just to highlight that it's now a problem again and no longer safe. But the scanner, that's the theory, does not make that distinction, because it doesn't understand that this is exactly the opposite of that. It undoes what we had in the mitigation. It understands this because it's a mitigation function. It needs to understand it to provide proper results. But if we undo the effect, the scanner, is stopped. So the idea is, the thesis of counter mitigation, the scanners revoke their tainted flag from variables once they know or see these variables have been run through a mitigation function. When this happens, the scanner no longer regards the input as tainted, And this is the cool thing, the issue is dropped. It's not downranked, it's dropped, because a mitigated issue is not something you want to show to the developers. So this is no longer an issue. All scanners we tested are affected by this. So again, I don't know what kind of scanners you're using. I don't tell which are the ones we tested, because we don't want to blame the vendor. You can try this. You will get the slides from the conference guys, and from there test, can this trick the scanner your company is using? This is not to blame the vendor. It's just that your companies then know, okay, there are some issues where we have to do other things than to use a scanner. So, and which brings me also to the conclusions. I still say that static code analysis tools are a good idea because they are able to efficiently spot accidental mistakes. That's what happens on a daily basis with developers. But they have limits, and it's important that the companies using them, or the security teams, know these limits. You need to know the limits, because if somebody intentionally introduces vulnerabilities, you are blind. You will not see that. So you need a second line of defense in your company apart from static code analysis, because otherwise you get infiltrated. And I showed 6 ways to do that. There are more, and there are many alternative ways to code what I coded here. So if you get creative, you can easily find other ways to modify these examples, even if the scanners find some to walk around with that. So, and the message I want to send here is static code analysis is good, yes, but it can't be the only line of defense your company uses against bad code. So, future research, before I conclude. The next thing we want to try, does it also work on dynamic application security testing? Does it work on interactive application security testing, or do we need other techniques? And the final thing, tricky, can we deceive the human tester or the code reviewer? Is there also code that can deceive the code reviewer? And the final goal is, can we find one code to deceive them all, against all types of scanners, against all types of users? That would be the perfect world. I doubt it works, but it may. So, not just at the end. Like I said, I come from Heidelberg. This is what my city looks like. And I was asked by the conference to give a small giveaway for the best question asked. Please bear with me, I turned that around, and I don't give it away for the best question asked, but for the best answer given from the next slide I have. This is a small snow orb from Heidelberg with the castle in it. Maybe if you are fond of snow orbs, then try to answer the next question. If you don't like snow orbs, you can answer it anyway and give it to someone else. Okay, so on deception, this is a self-check for all of you that are developers. This is written in Haskell. Probably not all of you are familiar with that. So I explain a little bit. I'm also not a Haskell coder. My friend HC in Germany coded that for me. What it does, it's again a web handler, and it receives input from a request, which is passed to the variable called user class, which is tainted here. This receives the input. And the next statement after that says, well, copy the value ls into user class. And finally, we store this into a system call. No? Again, we pass it to the operating system, which is a directory listing on Linux. So the self-check for you, is this code secure, yes or no? If you are a code auditor or code reviewer. Look at it for a minute, and then I ask to raise your hands. Who thinks this is secure, or who thinks there is a way around it?
A really nice snow globe.
Thank you. So as a little hint, everything above here has nothing to do with the problem. The problem is somewhere down here. I'm very interested now if I would use this code as a part of my malware, if a code reviewer would see the problem. it's a very devious thing I did here. So, anyone can comment on that? Is it or is it not? Here's the snow orb. Yes, please.
It's not the one-hot execution kind of situation as far as I can see, but anyways, maybe a very successful hot scanner would indicate that you're returning some internal information to the user.
Now,
And this result is going back to the user, and maybe it should not.
okay, so you said the code scanner would detect it. That may be possible, yes, I agree, the code scanner would detect it, but the question in this case is not does the code scanner detect it, but does a human being see the problem? Is this exploitable? Can I actually feed input to the server, which ends up in the system command? It's like a format hard drive or create user or whatever. Does it work? This is the input. It's going in here, and then we override it with ls. Can you do a system shutdown with that? The answer is yes, you can, but where is the problem? What could be the cause that this is actually a remote code execution? Pardon? A timing issue, good idea, but no, it isn't a timing issue. It's much simpler than that, but you can't see it. This is, again, now I attack the human, I attack your eyes, or your perception of what you see, because what you see is not what you get in this case. What is the problem here? So this is, by the way, how you can call this. Localhost 3000, because we started that, and then we append a command here, which is then passed to user class. The problem is tricky. That's the problem. User class and user class are not the same variable. They look the same, but in the first case, we use the capital letter C from the Latin alphabet. In the second, we use from the Russian alphabet the letter S, which is identical in view to this one. And here we have the Latin, and here we have the other. But as a human tester, you don't know that. We had to look quite a while to find a programming language that actually allows you to use Unicode and variable names. Most other languages we tried did not allow that. Haskell allows this. If you don't know that, you can fall prey to such an attack. Devious. So now I have to give this orb to an orb collector. Whoever likes it, from the Heidelberg Castle in Germany.
Well, I think for that attempt, that probably wins.
Yeah, of course,
right?
yeah. Then it goes to Israel. Okay, thank you. Okay, so thank you very much for your attention. If you have further questions, please ask. I don't know if there are any on the screen.
We actually do have quite a number of questions. I'm afraid we are out of time.
Oh.
So, but that's okay. That was a very good reverse answer session. We do have that one question. It's a good one. What we'll do, although because we're out of time, we'll take these questions off stage. Andreas will answer this question for anyone off stage so that we can move on with the schedule. But may I know who was the one who asked that question? Because we have a gift for you.
Right. The double winner.
All right, excellent. Okay, so the two neighbors then. And if possible, we'll do the answers outside. Anyone who wants to know the answer to that as well can join Andreas outside as well at the exhibition area to further the discussion. Thank you so much, Andreas, and audience. Thank you very much.
Thank you.